geometry of the bulk spacetime itself, and we saw that in order to do that, basically we had to, do a construction like this, where we ask what are the components of the Riemann tensor or the relevant projections of the full four-dimensional Riemann tensor when we express it in terms of things that are defined purely intrinsically to the hypersurface. And that's the notion that the bulk curvature can be decomposed into something purely intrinsic, and then the rest of it, which describes how a surface is bent, the extrinsic aspect of the curvature is captured by these extra terms over here involving our quantity KAB, which is called the extrinsic curvature, but is really understood as, being part of this decomposition of the full curvature in terms of the intrinsic and extrinsic pieces. And then, so all of these things, we sort of work them out in Gaussian normal coordinates. But after working this all out, what we did was to bootstrap ourselves to fully covariant expressions, and those are the result of all this. Combined with all of this, we had, for example, definitions for the induced metric on the hypersurface, which is something we talked about last week. And now we also have a definition for the components of the extrinsic curvature in terms of gradients of the normal vector projected down to the hypersurface. So basically, if I give you a spacetime and I give you a hypersurface in that spacetime, you can go ahead and calculate all of these things and verify, for example, that the Gauss-Kudacki equations are satisfied for that spacetime and for that hypersurface. What I want to talk about next, so in a few minutes, I'll look into some simple examples of how to compute extrinsic curvatures and just illustrate what they look like in various examples. So that will be useful just in terms of getting familiarity with these things. But I want to look into the consequences of the Gauss-Kudacki equation in the initial value formulation of general relativity, something that really brings these things to life and make them very important in the dynamical structure of GR. So what I want to talk about for the next few minutes is basically the initial value problem. In GR. And it turns out to be a very non-trivial thing. So I think we're all familiar with the basic ideas behind this. So I'll start easy with just the simple thing the simplest context for this, which comes from just mechanics. So when you try to find a solution of a mechanical system, of a mechanical system, well, typically you're dealing with, if we do, for example, the mechanics of a point particle, we would be given a second order differential equation for, say, one or more position quantities, and then we would make this equal to a force. So knowing the force allows us to calculate the acceleration. This is a system of second order differential equations, and we can find solutions. But if we want a unique solution, we have to specify initial values. So the solution is picked up only uniquely when you specify the initial value for the position and also the initial value for the velocity. So it's really this together that provides basically a well-posed problem. So if I only specify this differential equation, I can generate the general, a multitude of solutions. But if I specify the initial conditions, then I pick a unique solution and I have a well-posed problem, right? So that's familiar from a mechanical context. And the point is that we're dealing with second order differential equations in time. We need two pieces of initial data to pin down a unique solution. And in that context, we have complete freedom in picking this, complete freedom in picking that, and there's no obstacle in picking the initial conditions that you want. In the context of field theory, we're dealing with something already a little bit more complicated. So an example of a field theory would be just an ordinary scalar wave equation, say with a source term. So we might be dealing, for example, with a wave equation of the form minus dt squared acting on our scalar function would be equal to, let's say I should have written, I want to write down the wave equation. So we have the wave equation on the left-hand side being equal to some kind of source on the right-hand side. And this I can rewrite as, 2 partial derivative with respect to time being equal to, so I throw that over to the right-hand side, so I get the spatial gradients minus the known source term. So this also has the structure of a second-order differential equation in time, but now we're talking about partial differential equations. But more or less, this has the same structure as this. The only subtlety here is that, well, here instead of dealing with one or a finite number of degrees of freedom, here I'm dealing with a value for the scalar field at every spatial position. So it's an infinite dimensional system. We have an infinite number of degrees of freedom because we have to specify the field value not only at any time, but also at every spatial position. But other than that, the mathematical structure is exactly the same, well, more or less the same. But in order to, again, pick a unique solution out of all this, we have to specify initial values. And the initial values that I need to provide would be, for example, the field profiled at t equals 0 as a function of the spatial position. So I have to provide a full function of the spatial positions to specify initial values for this differential equation. And on top of that, I also need to provide the initial values for the time derivative of the scalar function at that time. So here I need to provide 2 full functions of the spatial positions, one representing the initial field configuration, the other one representing its velocity, so to speak. And the standard theorems on existence and uniqueness of solutions to partial differential equations would tell me that that I have a well-posed problem if I specify this evolution equation combined with those 2 pieces of initial data. So I need both. In the context of this simple wave equation, I again have complete freedom in picking this and complete freedom in picking that. So what we're trying to get at here is the equivalent of this, but in GR. And in GR, there are there are lots of complications that would arise. The basic ideas are the same, but we have to deal with the complications. One set of complications have to do with the fact that here I've written the wave equation in a very specific form that's not generally covariant. So, one step toward doing the GR case would be to say, well, can I redo this for the scalar field, say, but now in complete general covariance? So instead of picking the hypersurface t equals 0 in order to set up my initial data, I would have to do it on an arbitrary space-like surface, and I would have to choose, which initial data I want to put there in order to have a unique solution to my wave equation. So a fancier version of this in curved space-time would be to say that, well, the equation that I'm solving is really the equation that I should write in fully covariant form in terms of covariant derivatives and in terms of the curved space-time version of the wave operator, which is this combination of derivatives. So this is something that still mathematically has the structure of being second order in time, so I'm not changing anything about, in terms of its essential aspects. But in terms of specifying initial data, I cannot be, happy to say we're going to do it on a t equals 0 hypersurface. We have to say I'm going to need to do this over any space-like hypersurface that is given to us. So I cannot be picky regarding the choice of the initial surface. It has to be an arbitrary space-like hypersurface in space-time. So I have to provide initial data there, and I have to pick, the right initial data that will make this, this equation, this problem, well posed. Well, here it's not too difficult, so we can think of this hypersurface in the same way we thought of it before. We can say that, yes, we have coordinates x alpha in space-time, and we have coordinates ya on the hypersurface itself. We have a description of the hypersurface. We know how to calculate its normal. We know how to calculate everything else. And clearly, what I think it's pretty clear that what we would need to do in order to make this generally covariant would be to say that, well, of course, what I mean by that is the restriction of the scalar field on the hypersurface. So it would be the scalar field as evaluated on the hypersurface. So one piece of initial data that I need to place here would be the function of the coordinates on the hypersurface that represents my scalar field evaluated on the hypersurface. So basically, I specify the field configuration not at t equals 0 anymore, but I just do it everywhere on that space-like hypersurface. The other thing that I need to provide is the initial velocity, so to speak. And here, I think the only plausible candidate for what this might be in curved space-time would be the normal derivative of the scalar field on the hypersurface. So I need to specify that, but I also need to specify the normal component of the derivative of the scalar function evaluated on the hypersurface. And if I do it this way, I have a nice, at least I have a plausible description of the initial value problem for my wave, my curved space-time wave equation. And I have a way of setting this up in a nice geometrical way where I don't care about the identity of the initial hypersurface so long as it's a nice space-like surface. And then in terms of natural ways of describing the initial data in terms of the field configuration on the hypersurface and its normal derivative. And then, there are theorems and such that show that this, together with this and that, provide a well-posed initial value problem for the curved space-time wave equation. So one complication in GR would be to at least incorporate some of those ideas and try to see what else we need to do in order to provide a well-posed initial value problem in GR. Again, just as what we had here, here we have no, restriction in the freedom that we have to choose this function and that function. So we have complete freedom in the selection of the initial data in the context of the scalar wave equation. Okay, so now, there are two things that, so when we do this in GR, we have to think of all sorts of issues. And one issue that will arise is the fact that, we will be restricted in the freedom we have in selecting the initial data. So that's a feature of GR we're going to have to deal with. That turns out to be a consequence of the Gauss-Kudacki equations. That restriction in freedom is not unfamiliar. You also have it in E&M. So I'll make the parallel in just a second. But before I get to that, let's try to think about what's needed in order to do all of this in GR. So now it's not just an ordinary field theory. We're talking about doing this in GR. Well, presumably in GR, we have to incorporate at least that, right? So we're going to specify the initial value problem on a hypersurface. So first we pick a space-like hypersurface sigma, and we do what we were doing there. In GR, of course, the equivalent to this will be the full statement of the Einstein field equations. But it turns out, and we're gonna stare at the other equations we had before to recognize this, but it turns out that of all those equations over here, only a subset of the Einstein field equations have the character of being a time evolution equation in the same sense that we had here, where we could isolate the second time derivatives. And that's already something that we can see up here. There's a reason why I didn't erase the equations from this morning. When we look at this breakdown of the Einstein tensor in Gaussian coordinates, we recognize that only these guys over here have the appearance of a dt squared in them. So only those components of the Einstein tensor have second time derivatives in them. The other guys have a first derivative with respect to time buried in k, but they don't have second order derivatives acting on the metric anywhere. So of the full set of Einstein field equations, only the spatial components have this character of being evolution equations for the metric. So when I say that this is the analog of this, I'm oversimplifying the statement because it's only a subset of these equations that play a role in as time evolution equations. So I'll just indicate it this way. Okay, but now, so if we want an initial value formulation that makes any sense, we have to think about what we need to provide on the hypersurface as starting values for our time evolution equations. And if we're going to be inspired by the scalar wave example, we know that in some sense we need to provide initial values for the metric and initial values for its time derivative. That would be directly analogous. And we know it has to be something like that because we're dealing, as we see here, again with second order differential equations with respect to time. Well, it's second order with respect to everything, but in particular, it's second order with respect to time. Now, a very naive attempt to do this would be to say, okay, well, let's be inspired by these statements over here without the refinement that we incorporated just before. We could say that what we need to provide is the full metric at t equals 0 and its time derivative at t equals 0. That would be sort of the analog of the sort of unrefined statement that we made initially before we refined it to this level. And there are some problems with that. And the problem is that here I'm specifying too many components for the metric. Because out of those, I have 10 individual components. Only 6 of those characterize displacements only at t equals 0, spatial displacements. And the remaining 4 tell me something about displacements away from the hypersurface. The TT and the mixed T and spatial components really tell me something about what happens when I go off the hypersurface. They relate, space-time intervals to displacements that are away from the hypersurface. And basically, bottom line is that if I tried to specify all 10 components, I would be over-specifying things. I would be basically providing too much information, some of which may be inconsistent. So if we think a little bit more geometrically, I think it's pretty plausible, and it's got to be, that what we're allowed to specify on the hypersurface would be only those components of the metric that relate to displacements on the hypersurface. So basically what I'm saying is that what we need to provide as starting values for an evolution away from the hypersurface will be the induced metric, but only the induced metric, not the additional components that would characterize what happens when we go off the hypersurface. So basically, there's nothing very obvious about this, but if we're going to have an initial value formulation that has the same flavor as all this, I think it's plausible to think that the only thing that makes sense in terms of providing initial data would be to select the hypersurface and then select the metric on it, the induced metric on it. And then if we want something that plays the role of either this or that, well, we need something that has the flavor of being the time derivative of the metric or the normal derivative of the metric. And of all the things that we've encountered this morning, the only plausible thing is the extrinsic curvature. Because one way of writing this equation that's completely equivalent is to say that this is let's see, is there a half here? No, this is this is half the Lie derivative of the metric in the direction of the normal vector. projected down to the hypersurface. And written in this form, it's pretty clear that what I'm talking about when I'm talking about the extrinsic curvature is the normal derivative of the metric projected down to the hypersurface. So it's the normal derivative in the sense of being a Lie derivative. So you can think of it this way, or you can remember that in Gaussian coordinates, KAB really stood for the time derivative of the metric. And I think all of this tells us that it's plausible that in order to complete the specification of initial values on the hypersurface, we need to add KAB to HAB. And that should, if the mathematics works out, the specification of H and K on the hypersurface should be basically playing the role that these quantities play in the scalar case, but these should be the appropriate things to do in the GR problem. So the claim then is that the initial value problem in GR involves placing HAB and KAB, two symmetric tensor fields, on a space like hypersurface sigma. Once we have the initial metric and its initial time derivative, or once we have the specification of those two tensor fields on the initial surface, then the role of the Einstein field equations, or at least the appropriate subset of the Einstein field equations, will be to tell us what happens as we evolve forward in time or even backwards in time. Usually we do it forwards in time, but they will tell us how these things here will propagate forward in time to make up the full space-time metric away from the hypersurface. So then the name of the game is to do a time evolution with the Einstein field equations. Now, a major difference that we're facing here is that we don't have complete freedom in specifying those initial values. In fact, we're very restricted in doing that. We have to solve what are known as the constraint equations on the initial hypersurface in order to find physically available, physically appropriate values for the induced metric and the extrinsic curvature. And the constraint equations derive from those two, those pieces of the Einstein tensor. So let me where do I want to go? I'll go over there. So we have to satisfy the constraints, what are called the constraint equations. And the constraint equations tell us that those components of the Einstein tensor have to be equal to the appropriate components of the energy momentum tensor. So what I'm going to say is that, this has to be equal to 8 pi T mu nu n mu n nu by the Einstein field equations, and this has to be equal to 8 pi T mu alpha n mu E alpha, according to the Einstein field equations. So the constraint equations, if I just write them out completely, we have that the three-dimensional Ricci scalar associated with the induced metric minus these quadratic pieces in the extrinsic curvature have to be equal to 16 pi this particular component to the energy momentum tensor, the normal component to the energy momentum tensor, which has the physical interpretation of being the energy density on the hypersurface. And the other component of the other part of the constraint equations is the other one over here, which says that the divergence of k minus the derivative of trace k has to be equal to 8 pi, and now we have the normal tangential components of the energy momentum tensor. And this quantity here has the interpretation of being a flux of density or momentum density, sorry, a flux of momentum or momentum density on the hypersurface. So this is really a flux of energy, an energy flux, which is also the same thing as a momentum density in relativity. So we have to solve those equations because we have to solve all of Einstein field equations. But those equations don't have the flavor of being time evolution equations. Those equations are contained in the remaining components of the Einstein tensor. These components of the Einstein tensor basically are restrictions on h and k that you need to place in order to solve the field equations on the initial hypersurface. And they are restrictions on, they are a restriction on h and k because only the inducement, so those are, differential equations, or there are, restrictions on HAB, KAB that have to be satisfied in order to have valid initial values to do the rest of the evolution problem. So this is a restriction on H and K because, well, the left-hand sides involve, H through the Ricci scalar here involves K, but also H through raising and, lowering indices. These evolutions, these quantities here involve K obviously, but they're also H buried in the covariant derivatives and also in the raising of indices. So it's a rather intricate set of equations to be solved for H and K. Your H and K have to satisfy these things in order to solve those components of the Einstein field equations. And then the remaining components of the Einstein field equations are those that play the role of evolution equations for the metric and the extrinsic curvature. So going back to the scalar field example, what we find is that the role of this equation over here, which is the time evolution equation for the scalar field displayed by those guys over here, the purely spatial components of the Einstein field equations. What plays the role of this and this is H and K, but unlike the situation here, H and K have to be solutions to the constraint equations, which are derived from those components to the Einstein field equations. So when you look at the whole package of the Einstein field equations, well, there's really a separation between those pieces that basically are to be satisfied only on one hypersurface, or any hypersurface. So the equations that don't involve time derivatives, except so the equations that involve only h and its time derivative through k. So the equations that involve only h and k and no additional time derivatives have the flavor of being constraint equations. They don't they have to be solved on each hypersurface. And the remaining equations here, which have additional time derivatives in them, are the subset of the Einstein field equations that have the character of being time evolution equations for these things. And in fact, if you push this beyond what we've done here, something that we'll come back to when we do the 3+1 decomposition of the field equations, what you can, so these are the basically GTT equations, these are the GTA equations, and the GTB equations basically have the flavor of the JAB equations have the flavor of being time evolution equations for the extrinsic curvature, and we also we sort of have the, apart from a factor of 2, we have this definition of the extrinsic curvature in terms of the time derivative of the induced metric. Those equations supply the rest of it, the time evolution equation for KAB, so we can frame all of this into a nice dynamical system in first order form, where the first order, the first time derivative of the metric gives me K, and we have all this mess on the right-hand side plus the, the TAB component giving me the right-hand side here for the time evolution of KAB. Yep?
How about our initial freedom to choose the slicing conditions, in other words? So you said that the constraint equations and the evolution equations have nicely their parallels in Newtonian physics, those two sets.
Yep.
So what about the freedom in choosing your hypersurfaces initially?
That freedom is complete. So that's a good question. So, so when I did it for the scalar wave equation, naively, or, I could do it as, on a t equals 0 hypersurface, but in fact here we recognize that we can set up initial data on any space-like hypersurface. Well, the same is true in GR. So I can select this hypersurface completely, freely. I have no restriction on the choice of hypersurface, but once I've selected the hypersurface, then, when I place HAB and KAB on it, then they have to be solutions to the constraint equations. So, other questions?
And in this course, will we talk about which slicing conditions are good in which physical situations, or would we limit ourselves to the case of black holes and the event horizon of black holes?
Yeah, so if this were a course in numerical relativity, the choice of slicing condition would be very critical to the success of a numerical evolution. So numerical relativists have invested a lot of effort in trying to understand, how to make good choices of slicings. But really, there's no recipe. I mean, you just, so basically it really depends on what the spacetime wants to do. And what you have to do is to make sure that the slicing that you adopt in your numerical evolution is adapted to what the dynamics of the spacetime is. And that's something that usually you recognize after running the simulation. You would know all about that, right? So typically people try to run a simulation and they end up with, the code crashing because the coordinates go crazy. So they have to look at this and then they say, oh, okay, well, if I were to do this instead, apply this slicing condition instead, maybe I would, do better. Then they try that and they see that, yes, it works better, but it still, crashes after a while. Then they refine this so the selection of good slicing conditions is something that is much more of an art than a science, and that's usually based on tons of experience of people, witnessing their codes crashing all the time and, and finding cures for that. So certainly I won't say anything about that, in the rest of the course. Okay, so the important message here is that, so I haven't really proved anything except to derive the expressions for the constraint equations, but then the theorems would say that, given suitable initial data on a selected hypersurface, the hypersurface has to be space-like, given suitable initial data in the form of a 3-tensor that we call the induced metric, and the 3-tensor we call the extrinsic curvature. By suitable, I mean given a solution to the constraint equations, then the theorem says that given suitable initial data for these two things, there's a unique evolution for the metric away from the hypersurface modulo the freedom to do coordinate transformation. So there's always this, this caveat that the solution is unique up to diffeomorphism, so you have to retain the freedom to do coordinate transformations. But the point is that modulo this, given suitable initial data for H and K, this is a well-posed problem. There is a unique solution away from the hypersurface such that, the metric on the hypersurface and its time derivative will agree with your initial values. And the point is that this is just precisely the right amount of initial data you need to provide to ensure uniqueness modulo diffeomorphisms. You don't need to specify more than this. It would be wrong to specify more than that. This is exactly what you need to provide. And then I think the best way to to analyze all of this is to cast the Einstein field equations in the form I was suggesting before, in the form of this dynamical system where you have first order equations, one for h in terms of k, and one for k in terms of everything else. And those are equations that can be systematically, at least in principle, evolved forward in time. And that's the whole business behind the 3+1 decomposition, or the ADM decomposition, something that we'll come back to later on. But again, the very important message here is that when we look at the full set of Einstein field equations, they look very pretty when you look at, when you write them out this way. But when you unravel this, you have to recognize that, all the equations in the set are not doing the same thing. They're not to be treated equally. We have those two equations that are meant to provide constraints on initial data, and we have those equations that have the role of providing time evolution equations for those values. So the split of the Einstein field equations is very important in order to, to formulate the initial value problem in a way that, that is well posed and makes sense. Obviously, in all this, the extrinsic curvature plays a very important role. You have to solve both for the induced metric and the extrinsic curvature by solving the constraint equations in order to do anything from that. All right? So that's my discussion of the constraint equations. In the book, I do a little bit more than this. I give you a little bit of a flavor. I try to find solutions of these things, and there's been a whole industry in numerical relativity, especially in trying to come up with good ways of finding solution to the initial value problem. So there's a class of solutions that's well known called the Bowen-York solutions to the constraint equations that describe two bodies that could be black holes in orbit around each other. So it's a very powerful way of setting up initial data for numerical simulations, because you have a fairly well, sort of, I want to say easy, but it's not that easy. I mean, you have sort of nice parameterized solutions of your constraint equations. Well, these ones are easy to solve. These ones are, still have to be solved numerically. So it's still a bit of a mess. But anyway, you have a nice characterization of your initial data in terms of, two positions, two masses, two linear momentum vectors, two spins, and things like that. So you can capture, the initial state of a binary system like this using their solutions. It's not the most general solution, so it's just particular solutions to the constraint equations, but they have a nice flavor to them, so they've been very popular. But the point is that when you set up initial data for numerical evolution, you have to solve those equations. There's no obstacle. There's no alternative. You really have to deal with that. So again, in the book, I give you a little bit more of a discussion of this, but I think I'll just cut this short here and basically say that, this is something that's part of GR, something that needs to be understood and dealt with in many situations, but I won't go into any more details than that. Any questions before I do something else? What I want to do, just to try to firm up our understanding of these things and firm up some intuition about all of this, I want to look at specific examples of calculating extrinsic curvatures, because that's a new quantity that we introduced today. So I want to give you lots of different examples of extrinsic curvatures for different situations so that we can start to see what all of this means. So that's what I'll do in the next few minutes. So we'll do some simple things, just again to gain some useful intuition. So I won't need this anymore. I should have kept those up because I'll refer to that. That's the glamorous part of the job. Okay, so let's look at examples of extrinsic curvature. And I'll start with two-dimensional surfaces embedded in three-dimensional space, and then I'll do three-dimensional surfaces embedded in space-time. So the dimensionality of the bulk relative to the dimensionality of the bulk. So I've worked out everything in terms of four-dimensional space-times, but everything carries over unchanged if you just do two-dimensional surface embedded in three-dimensional spaces. Everything follows. It's exactly the same thing, so there's no need to be confined to 4 dimensions or 3 dimensions. I could do, 26-dimensional bulks and, 25-dimensional surfaces in them. It would be exactly the same thing. So let's do a 2D sphere in 3D space. And I'll do it in flat space, really, to do everything simple. So here's my three-dimensional space, and I'll use Cartesian coordinates. And here's my surface, and that's a sphere of radius r. And what I want to do is to work out, the induced metric and the extrinsic curvature on that sphere and see how that relates to the Gauss-Cadazzi equations and all of this. So my bulk coordinates are going to be the Cartesian coordinates of my three-dimensional space. And what I'll do on the sphere is to use the usual polar coordinates, spherical polar coordinates. So I'll use my two angles, theta and phi, as intrinsic coordinates on the sphere. So to have a full description of the hypersurface, I need to provide the function phi, and I need to provide the parametric equations that describe, the constant, the coordinate lines on the sphere. So I need to do that. So the function phi, I can take to be the one that says that the distance on the sphere is equal to r. And my surface then will be where phi is equal to 0. And the parametric relations is the one that says that, well, x is going to be r times sine theta cosine phi. Y is equal to r sine phi, sine theta sine phi. And z is equal to r cosine theta. And usually that's the hard part of the problem, to just find a good intrinsic coordinate system on the surface and then find all those relations. Once you have that, you have everything. So from the function phi, we can get the normal vector. So the normal vector will be proportional to the gradient of phi, which means that it will be proportional to x, y, and z. And all I have to do then is to normalize. So it's going to be x over r, y over r, z over r. So those are the components of my normal vector. And then I will have two tangent vectors in this case. E theta, which will be the partial derivative of x, y, and z relative to theta. So that will give me r cos theta cos phi in the x direction. r cos theta sine phi in the y direction, and minus r sine theta in the z direction. So that's my first tangent vector. And the second tangent vector is the derivative of x, y, and z in the direction of phi. So now we get minus r sine theta sine phi. We get r sine theta cosine phi, and 0. And that's a complete basis, and we can calculate everything from that. So if I want to calculate the induced metric on a hypersurface, I just take the flat metric of 3D space, and I project it down to the hypersurface using my tangent vectors. And when you do this calculation, well, it's pretty simple. You just take inner products between all of those vectors. So it's pretty simple. You just work it out, and you find that h theta theta is, of course, r squared. H theta phi is 0, and h phi phi is r squared sine squared theta. So we have the usual metric on the round sphere. You can calculate the extrinsic curvature, and now what you have to do is to take the gradient of the normal vector, and then you project this down to the sphere. And in this case, well, that's pretty easy because the metric in the space-time is the Euclidean metric of Cartesian coordinates. So here there's no distinction between the covariant derivative and partial derivatives. And well, partial derivatives of the normal vector will be constants. So if I differentiate with respect to x, I get 1 here, 1 over r, and so on and so forth. So all of those computations are pretty easy to do. And the last thing you need to do is to do the projection. And when you do that, again, that's very simple. It just follows after a couple of lines of algebra. You find that k theta theta is equal to r, that k theta phi is equal to 0, and that k phi phi is equal to r sine squared theta. And a nice way of summarizing this is to say that for the sphere, KAB is 1 over r HAB. And that's not an accident. That's really an outcome of the spherical symmetry. So when you have something so symmetrical as the sphere, while you have one tensor on the sphere that's given, that's the induced metric on the sphere, pretty much any other tensor on the sphere will have to be proportional to that tensor. And here we have a rank 2 tensor being proportional to the other available rank 2 tensor, and this just sets the proportionality between the two. You have a question?
And it's a static situation, right?
Oh yeah.
So that's why we don't time.
Well, here, so it's a three-dimensional example, right? So I'm not working in space-time. I'm working in space.
Okay.
Yeah.
Sorry.
So yeah. So it's a very simple thing. So what we find out here is that the extrinsic curvature of a sphere is something that decreases as you make the sphere larger, and that's something that I think has some So if you imagine the sphere being embedded in the space-time, so the extrinsic curvature really measures the amount of bending. If you make the sphere very large, the amount of bending becomes increasingly small. And in the limit where r goes to infinity, well, you just don't see the curvature anymore. You don't see the bending, and that's the limit where r goes to 0. Do I see a puzzled look on your face? Yeah.
I mean, it's true when you compare it with the metric, but
Yeah.
the components of k itself go up, right?
Yeah, and that's a very good point. So when you compare things, you have to be careful, when you look at components, it can be very deceptive because the components of a tensor are a reflection of the coordinate system more than anything else. A comparison between tensors is something that's really intrinsic to the quantities themselves. So I would say that this comparison is meaningful. Making statements about the coordinate components is something that, well, would have to be a little bit dangerous. Okay, so that's the extrinsic curvature. We can ask what is the intrinsic curvature on the sphere. So I won't work this out in any detail, but the Riemann tensor of that two-dimensional surface goes as 1 over r squared. And it's proportional to the metric, so it has this nice combination of metric tensors. So that's another statement that any tensor on the sphere will have to be proportional in some way to the metric tensor. And here, because we're talking about a 4-index object, it has to involve products of the metric. That's the structure that you get when you have a maximally symmetric space. The Riemann tensor always turns out to be proportional to the metric in this way. And the coefficient in front is basically 1 over the radius of curvature, or, well, it's the scalar component of the Riemann tensor, the scalar part of the Riemann tensor. And well, that's interesting. So that says again that so the extrinsic curvature decreases as 1 over r. The intrinsic curvature decreases as 1 over r squared. And all of this makes sense because according to the Gauss-Codazzi equation, so according to Gauss-Codazzi, the bulk curvature, which has to be 0 because we're dealing with space, with 3-dimensional flat space, let me call it the 3 curvature evaluated on the surface has to be equal to the intrinsic curvature plus the stuff that comes from the extrinsic curvature. Or is it minus? Oh, sorry. That made no sense. It has to be KAD. According to Gauss-Codazzi, this is KAD KBC minus KAC KBD. So we know the left-hand side is 0. What we need is to have cancellation between intrinsic and extrinsic curvatures coming from the surface. And sure enough, when you put it all together, you find that this, so KAD KBC basically gives you this term again. KAC KBD gives you this term again, so you get nice cancellations on the right-hand side. And it had to be like this because the bulk curvature is 0 in this case. So in this case, the intrinsic curvature and the extrinsic curvature conspire to give no curvature at all in the bulk. So in a sense, we see here that in a case where the bulk curvature is 0, while the extrinsic curvature has to be something like the square root of the intrinsic curvature, or said differently, the intrinsic curvature has to be something like the square of the extrinsic curvature in order to have the right balance. And that's what we see here. The intrinsic curvature goes as 1 over r squared. The extrinsic curvature goes as 1 over r. All right? So that's my first example. All the computations here are very simple, and you're welcome to try this on your own time. Let's do another example. So instead of a sphere, I'll just do a cylinder, just to see how things change. So here we'll have a 2D cylinder in 3D flat space. So now it's a little bit different, but similar. So here's our 3-dimensional space, X, Y, and Z. And here's our cylinder. And here I'm assuming it's just an infinitely long cylinder. I don't want to put caps on it. And a cylinder of radius r. So again, the starting point here is that we're presented with a hypersurface. We need to describe it, and we need to describe it in two ways. So we have to provide the function phi, and then we have to provide the intrinsic coordinates and the relationship. So my extrinsic coordinates, my bulk coordinates, are still going to be x, y, and z. And for my intrinsic coordinates, what I'll do is to pick z again, because it's a nice coordinate on the cylinder, and then I'll pick phi, which is the angle around the cylinder. And so my function phi is going to be the statement that x squared plus y squared minus r squared is going to be 0. So that's the statement that the radius perpendicular to the axis is r. And the parametric description is going to be to say that x is going to be r cosine phi, y is going to be r sine phi, and z, of course, is going to be z. So that's basically paralleling what we did in the case of the sphere, but now we do it for a cylinder, and well, presumably we'll get some slightly different results. From all this, we calculate the basis vectors. So the basis vector is more or less the same story. So it's going to be proportional to the gradient of phi. So we'll still get an x over r in the x direction, a y over r in the y direction, but there's no gradient along z, so this component is 0. For the tangent vector along z, well, we get 0, 0, 1. For the tangent vector along phi, we get the derivative of these guys with respect to phi, so we get minus r sine phi, r cosine phi, and 0. So from that, we can get the induced metric, and I'll just write it in this form. So the line element on the cylinder, when you do the calculation, you find that it's going to be dz squared plus r squared d phi squared. Basically, it's just a circle crossed with a line, so you get the usual dz squared along the line and the usual r d phi along the circle. So nothing surprising here. KAB, here I have to list the components. When you calculate the components of the extrinsic curvature, you get 0 for z, you get 0 for z phi, and you get k phi phi being equal to r. And here we're dealing with a case where we don't have proportionality between KAB and HAB, and that's because we're not dealing with a completely spherical space like the sphere. We have something which obviously has two very different directions in it. So here I don't have a fancier way of writing out the components of the extrinsic curvature. I just write it like this as a listing of components. But the interesting part is that if you compare with what we had before, well, the phi phi component is comparable except for the sign, but we don't have we don't have other non-zero components for the extrinsic curvature. Something I could have written here is that the trace of the extrinsic curvature is 3 times 1 over r, because when I take the trace of the induced metric, I get 3. And I get the 1 over r, so I get 3 times over r. According to this result, the trace of the extrinsic curvature, well, there's only one term in it, so it's going to be 1 over r instead of 3 over r. What all of this is telling us is that whereas in the sphere there was curvature in all directions, for the cylinder, there's only curvature along the circle. I'm talking about extrinsic curvature. There's only extrinsic curvature along the circle. There's no curvature along the axis. So that basically turns the 3 into a 1 over here, and it produces those 0 components. All right. If you work out the next thing, the intrinsic curvature, you find that it's 0. As I think we talked about before, when you roll up a piece of paper into a cylinder, you're not producing intrinsic curvature. All you're generating is extrinsic curvature along the circle and no extrinsic curvature along the axis. So the 3 curvature, or the surface curvature, the intrinsic curvature is 0 in this case. And that's compatible with the Gauss-Cadazzi equations because, well, basically, the left-hand side has to be 0. This by itself is 0. And what you get then is, just compensation between those two terms. So this will always be equal to that. And with the minus sign, you basically produce cancellation. So this equals that. And all of this gives you 0. All right. So those are 2 pretty simple examples. Let's do something in space-time now. So what I'll do now is to do something in an expanding universe. And so now we'll see what time, time does in all of these things. So my third example is FRW and we'll take a t equal constant surface. So we're talking about the metric of an expanding universe. So in space-time, the metric is going to be minus dt squared plus a squared of t times dx squared, dy squared, dz squared. And here, for simplicity, I'm just taking the spatial sections of my FRW metric to be flat. This, by the way, is an example of a metric written in Gaussian coordinates. And here the Gaussian coordinates apply globally in the space-time. So it's a nice, simple, symmetric space-time where this is possible. What I want to do is to take a surface t equal constant. And I need to describe this surface. And of course, the simple description will be to say that the function phi is going to be t minus that constant, so that phi is equal to 0 on the hypersurface. So that's one of the 2 descriptions. And then, well, in my space-time, I have t, x, y, and z as space-time coordinates. On my hypersurface, well, x, y, and z are sort of already selected for us. It would be very sort of foolish to do something else. So on the hypersurface itself, I'll just use x, y, and z, because clearly that's the simplest thing I can do. The parametric equations, I don't even need to write them down, are just saying that, well, x is equal to x, y is equal to y, z is equal to z. So that's as trivial as you can make it. The normal is going to be here. Here the normal is going to be proportional to minus the gradient of the scalar function, because that's the epsilon that we have to introduce. So in this case, because we're talking about a space-like surface, well, typically we introduce a minus sign. So I'll just put it here. So that's our unit normal, so that the vector is future pointing when I raise the index. And then, of course, E alpha x is going to be equal to 0, 1, 0, 0. E alpha y is going to be 0, 0, 1, 0. E alpha z is going to be 0, 0, 0, 1. Well, if we calculate the induced metric, in this case it's very simple, because all I have to do to get the induced metric on a hypersurface is to kill off the dt over here. So we're talking about a t equal constant surface. So the ds squared restricted to the hypersurface is going to be what's left over. So we get our scale factor evaluated at that time, multiplying the flat metric. So now A is to be evaluated at that specific time, right? So I should say t equals 0 and call that t equals t naught. So this is t equals t naught, just to make it clear. So that's the induced metric. If we calculate the extrinsic curvature for that, what we get for components are going to be these. Kxx is going to be equal to A times A dot evaluated at t equals 0. And that's going to be equal to Kxx to Kyy, and that's going to be equal to Kzz, and all the other ones are going to be 0. So here we have a very symmetrical space where all the directions are equivalent. So we get that all the components of the metric are the same in each direction, and in the same way, all the components of the extrinsic curvature are equal in all the directions. So a way of summarizing all this is to say that KAB is going to be A dot over A evaluated at t equals t naught times the induced metric. And the trace of K, the trace of KAB is going to be 3 times A dot over A evaluated at t equals t naught. So, something interesting here. When the universe is expanding, the coefficient is positive, and K is basically a positive definite vector tensor. When the universe is collapsing, A dot is negative, and that means that the sign of KAB is different. It becomes a negative valued tensor. Well, that really meshes with our, naive association, or, our intuitive association between KAB and the rate of change of the metric, right? So, especially in this coordinate system, that connection is very transparent. If the universe is expanding, that means that the metric is increasing, right? It's producing more volume as the universe expands, and so that means that the rate of change of the metric is positive, and that gives rise to a positive extrinsic curvature. When the universe is collapsing, well, it's the other way around, where the universe is shrinking in size, the rate of change of the metric is decreasing, and that produces a negative extrinsic curvature in those recollapsing situations. An interesting thing happens when you have an expanding universe that stops expanding and starts collapsing. When you have, a maximum expansion that turns into a recollapse. There are certainly solutions to the Einstein field equations if you put in the right, the right K and the right, components to the energy momentum tensor that have, a phase of expansion leading to a maximum expansion and then a recollapsing scenario from there. At those situations where the expansion turns around, A dot obviously is 0. So that's a turning point in the evolution of the universe. And at those points, at those moments in time, the extrinsic curvature vanishes. So the extrinsic curvature goes from being positive, and it decreases in size, and then it changes sign, and it becomes negative. That time where you have, expansion turning into recollapse is a moment of time symmetry in the evolution of the universe. So the evolution to the future will look like a mirror image or the time reversal of the evolution to the past. So that defines a moment of time symmetry in the evolution of a universe. And more generally speaking, whenever you have a situation where KAB vanishes, you have a situation where the metric has no time derivative at this moment. And that also corresponds to a moment of time symmetry. It's like having a turning point where, an initial velocity that's positive turns into a negative, So a turning point in mechanics. So if you have a potential that looks like this, and you have motion between two turning points, what it means is that, for a while you have positive velocity that turns into negative velocity, that turns back into positive velocity, negative velocity. So you keep on alternating between two turning points. And every time you hit a turning point, you hit a moment where the evolution to the past and the evolution to the future is time symmetric. So the turning point in mechanics is a moment where the evolution is time symmetric. It's a moment of time symmetry. Well, here we have the same thing going on here in this example, but more generally speaking, whenever you're dealing with a hypersurface such that KAB is 0, a hypersurface with no extrinsic curvature, that's a hypersurface where the time derivative or the normal derivative of the metric vanishes, and that means that whatever it's going to do in the future has to mirror what it was doing in the past. You have to have a moment of time symmetry. If you have a whole succession of surfaces where KAB is 0, you have a whole succession of moments of time symmetry. That's when you have a static universe. Nothing happens, right? Nothing ever changes with time. That's a situation where all your t equal constant surfaces will be moments of time symmetry, and each of those will have 0 extrinsic curvature, right? So that's a neat example for that because, it tells us something about the relationship between the dynamics and what happens to the sign of the extrinsic curvature. All right, you can play around with the Gauss-Codazzi identities here and verify that, well, in this case, of course, in the bulk, we don't have a vanishing curvature. So in this case, we have the interesting situation where there's curvature in the bulk, but there's no intrinsic curvature on our surfaces because all of those surfaces are flat. So when the metric is restricted to a moment in time, what you get is a constant factor times the flat metric that is still a flat metric. So here's a case where the intrinsic curvature is 0. The bulk curvature is not 0. But in this case, the bulk curvature is completely made up from external curvature, from extrinsic curvature. So it's a different situation from what we had before. So you can work out the details of this and make sure that the Gauss-Codazzi equations are verified. Yep.
So this is the shell, the spherical shell expanding, or the inverse. So what if the shell is massive? Would it result? Intuition says it would result in something like a Schwarzschild because of the breakups.
Okay, so this is a cosmological scenario where you have uniform density everywhere, right? So it's a constant density everywhere. So it's really not a shell. It's really, the whole space expanding and recollapsing in a completely uniform way.
Yes.
If you were to do a shell, I think you would have in mind something where, you would have, I don't know, either you're talking about a spherical object that has, a non-zero density inside and a zero density outside. And if you were to let that collapse, of course, you would produce a black hole or something like that, but that's a very different situation, right? But if you were talking about, for example, a pulsating star, so you have a pulsating star that, is expanding, then recollapsing, then expanding, then recollapsing, not to 0 radius, but it's, it's oscillating between a minimum radius and a maximum radius. Well, every time you go from expanding to contracting to expansion to contraction, those turning points would be moments of time symmetry. And those, moments of time would also have a 0 extrinsic curvature.
But about the the massive shell, I didn't mean it collapses into a black hole, but even taking the shell itself, in Newtonian physics, it's equivalent to a point mass.
Yeah.
And here, I guess, if I'm right, I don't know, according to Birkhoff's theorem, should still be equivalent to a point mass.
Yep.
So if you take just a massive shell moving
Mm-hmm.
time, it should just be equivalent to the metric of the point mass.
Oh, outside the shell.
Outside the shell.
Yeah. Yeah.
And I don't know whether it's the right place to ask, but it's a GR course. I was always confused about this because I always found it difficult to understand how a massive shell moving wouldn't affect the geometry, wouldn't change the geometry outside.
Outside the shell. It's the beauty of spherical symmetry. So that statement is true even in Newtonian mechanics, right? So if you have if you have a pulsating star in Newtonian mechanics, the field outside is always gm over r and nothing else. It doesn't know the field outside doesn't know anything about the internal motions of the star. And in GR you have the same thing by virtue of Birkhoff's theorem. What it means physically is that a pulsating star or anything that has motion, so long as it's spherically symmetric, doesn't emit gravitational waves, so that there's nothing to propagate from where the motion takes place to the outside. So the outside is always oblivious to what's going on.
But sorry, maybe it wasn't the right place to.
It's a good segue into my next example where we'll do Schwarzschild. So I want to do Schwarzschild. And Schwarzschild could be basically the external geometry of any distribution of mass that's spherically symmetric. So, next example, we'll take Schwarzschild, and we'll pick a t equal constant surface of Schwarzschild. So in spacetime, the full metric in spacetime will have the usual Schwarzschild form. Where f's minus 2m over r. And I'm picking a t equal constant surface. So in spacetime, my coordinates are going to be t, r, theta, and phi. And on my hypersurface, well, because the hypersurface is very simple, I'll just pick the remaining coordinates on the hypersurface, r, theta, and phi. The description of the hypersurface is to say that we're talking about a t equal constant surface, so I'll take it to be t minus t naught. And my parametric description is very simple. We just say that r is equal to r, theta is equal to theta, phi is equal to phi. The normal vector to the hypersurface will only have an entry along time, but we have to normalize it. And that means that we're going to have to involve the function f in the normalization condition. So when you work out the details, you find that the time entry is no longer 1 because we have a coefficient here in terms of dt squared. So the time entry for the normal vector is minus the square root of f. And all the other entries are 0. The other vectors, e alpha r, well, this one will only have an entry along r. This one will only have an entry along theta. And that one will only have an entry along phi. So, with all of that, we find that, well, the induced metric on the hypersurface is going to be basically what we get when we get rid of the dt squared in the four-dimensional metric. So we get f minus 1 d r squared plus the r squared d omega squared from the two spheres. And when we calculate the extrinsic curvature, which again we get by calculating the gradient of the normal vector and projecting, well, that requires a calculation because, well, here the component of the normal vector is non-trivial. The crystal symbols are non-trivial in this case, but when you do the calculation, you find that all components vanish. And that's not surprising because we know that KAB is supposed to calculate, to capture the rate of change of the metric with respect to time. And here we have a static metric that has no time dependence. And it was a pretty good expectation that this should turn out to be 0. And sure enough, it does turn out to be 0. So one way to describe this is to say that the Schwarzschild metric here can be foliated into a bunch of t equal constant surfaces. The spacetime is static, therefore each one of those t equal constant surfaces is a moment of time symmetry. So on each of those hypersurface, KAB has to be equal to 0. So if KAB is equal to 0 only on one hypersurface, then what we have is an isolated moment of time symmetry, and KAB may be non-zero to the future and to the past. When we have a whole stack of hypersurfaces and KAB is equal to 0 on all of them, we have a static spacetime. We have no change in the geometry whatsoever. All right, so any questions about this? So I think in the current homework assignment, I'm asking you to calculate these things in other contexts, so other examples, but now you sort of know the machinery that's associated with that. So what's the message? So I have just a few more minutes to summarize what we've learned today. We've done a lot of work today, actually. We've covered a lot of stuff today. The central message is that when we have a hypersurface embedded in space-time, we have a complete characterization of that surface if we know its intrinsic metric. That gives us everything that has to do with its intrinsic properties, including its intrinsic curvature. But if we want to describe how it's bending in the bulk space-time, the extrinsic aspects of the geometry, that role is played by the extrinsic curvature, and the extrinsic curvature is something that plays a very, very important role in differential geometry, first of all, but also in GR, and we saw what role it plays in terms of the initial value formulation. It plays a very central role there. And it's something that you really need to know something about. So today, I mean, I've pretty much I gave you the essential aspects of this today in terms of where it fits and what role it plays in GR. There's a lot more that could be said about this, but because I want to get to black holes at some point, I'm going to have to cut it short. One aspect that I won't discuss, but you'll find in the book, is that you can involve the induced metric H and the extrinsic curvature K into a very nice geometrical formulation of junction conditions in GR. So something that would be analogous to what you do in E&M, where you say that if you have a surface layer of charge, you know that the normal component to the electric field will be discontinuous because of that distribution of charge, but you know that the tangential components of the electric field will be continuous across that surface layer. Well, those are the rules that allow you to glue two solutions to Maxwell's equations together on a hypersurface. And if the junction of those two solutions is completely smooth, then you know that at the transition surface between the two, you don't have anything. You don't have any distribution of charge. If you have a junction such that the tangential components ends up being discontinuous, like that, well, here it's continuous. So that's my hypersurface. If my E field is like this, it's fine. If my E field is like that, it's not fine. It's a discontinuous configuration. That says that this violates Maxwell's equations, and it's not a valid way of gluing two solutions. If you find that you have tangential components that are continuous in your junction, then you have a valid solution to Maxwell's equations, so you've successfully joined two solutions across a boundary. If you have a discontinuity in the normal component like this, then you know that on that boundary you have a surface layer of charge. So that's pretty familiar from E&M. Well, you can do that in GR. You can take, let's say, one solution on one side of the hypersurface, another solution to Einstein's equations on the other side of the hypersurface, and you can decide based on the rules that can be formulated whether or not that junction is actually legal, whether that junction is, satisfies the Einstein field equations across the boundary. One thing you need to have is a continuous intrinsic geometry for the boundary. So the induced metric from this side and the induced metric from that side have to agree, otherwise the geometry of that boundary would be ambiguous. It wouldn't make any sense. So the induced metric has to be continuous on each side, and if you don't have that, you don't have a valid solution for your joint solutions. If you have a discontinuity in the extrinsic curvature, that means that at the boundary, you have to have a surface layer of matter. If the joint is such that both H and K are continuous, then that means that there's really nothing physical going on at the boundary. You've just glued two solutions, and there's nothing in between to glue them. It's just a very continuous joining of the two solutions. If you have a jump in the extrinsic curvature, that means that the joint is valid, but to make it happen, to make it a valid joint, you had to put a boundary layer of matter in between. And that's analogous to having a surface layer of charge when you have a discontinuity in the normal component to the electric field. So there's a beautiful literature on this that I captured in the book. In the book, I also go beyond this, and I do surface layers and junction conditions for null hypersurfaces. So all our beloved subtleties of the null case come back in that case. I won't say anything about that in the course because, again, in the interest of time, I really want to move on and go toward doing black holes. But I'm inviting you to read about this. There are certainly lots of applications in GR where it's very advantageous to have models of spacetimes where you have joint solutions like this. Here's my solution for the stellar interior. Here's my Schwarzschild exterior. Let's join them and decide whether or not there's something funny going on at the surface. That's those are very so the idea of merging solutions like this or joining solutions across a common boundary, that's a very powerful tool in GR that has been used a lot in the literature. So I'm inviting you to have a look at this, but on your own time. What I'll do next week is to spend a little bit of time talking about the Lagrangian and Hamiltonian formulations of GR. And when we have done that, then we'll be ready to do black holes in full swing. And that's how we'll finish off the semester. So that's all for today. Thank you very much.